2. Yeah, we all know that. We've been there, done it. That's what's happening here. We are not going to leave a carbonyl behind with a powerful nucleophile reacting agent. Number 10. I see a carbonyl with a leaving group. How many people recognize there's a leaving group there? I know it's in a ring, but it's still a leaving group. Okay, I go over and I see a strong nucleophile hydroxide. So I'm just going to go attack the carbonyl, open the carbonyl, close the carbonyl, whoosh, I open up the ring. Okay, they don't have any acid showing there at the end. You could either leave it as an O- for the alcohol part, or you could say it goes on and reacts with water and gets an H there and makes more hydroxide. Either one of those would be a wonderful answer. If they had a step 2 that put acid in there, then you would definitely switch the O-. But I would take either one as a very well-reasoned answer. Okay, number 11. Nitrogen's always linked. How many people truly get nervous when they see nitrogens?
Hate them.
You don't need to. They're just nucleophiles. If in doubt, put an O there and think about what the O did. So I see a carbonyl with a leaving group. Okay, granted, my warning bells might go off. Is this a particularly good leaving group? No. When the nitrogen or even the ester is sitting there as a leaving group, you don't want to just push it off without thinking. I mean, it is not the best leaving group in the world. So you want to make sure that you're supposed to push it off. The nitrogen thing in particular, the only thing that you can do is push off and make carboxylic acids or carboxylates. So I don't see a nucleophile though. It's hidden in there in the dilute acid. So water attacks the carbonyl, opens the carbonyl after we've made it succeed. We need to put H on the nitrogen so it's a leaving group, close up one of the carbonyls, open the group. So this is a ring or ring. Basically 10 and 11 are exactly the same thing. They're pushers. One uses the strong nucleophile, one uses the weak nucleophile. We would call both of these hydrolysis reactions. Do you see how the flowchart, the principles lead us into that? How many of you have your flowcharts down cold at this point? How many of you will have them down really, really well by Monday? How many people are convinced if you have them down really well, you're less likely to get stuck on Monday? Does it give you a place to start? If you have a place to start, I can give you partial credit. If you're just throwing nucleophiles and things, I'm going to take Motrin and you're not going to have a good grade. The more Motrin I take, the worse the grades are going to be. Number 12. Well, the first thing I see is an alcohol. I don't see a carbonyl, so I'm tempted to think first semester reaction, but I look over the arrow and I see a carbonyl. It's a very common way to trick students up. It's with carbonyl, the arrow, and the nucleophile in the reactant spot, because we are visuals. Learn organic chemistry by visual. You know, where do I see it? So what I see is there's a carbonyl over the arrow. It doesn't have a leaving group. Hydroxide, not the world's best leaving group. Okay, but it's possible to push. I see some acid, I see some alcohol. The alcohol is probably the nucleophile they're interested in using rather than water, because if they use water as a nucleophile, they're going to make a bunch of hydrates or carboxylic acids back. So we're probably going to use the alcohol as a nucleophile. So I'm going to make a sexy carbonyl and a carboxylic acid, pack the carbonyl, open the carbonyl, close the carbonyl, push. Watch my protons. This is the Fischer esterification. Super, super commonly tested Fischer esterification. Yes?
How can you push off the OH in a
You don't push it off and put a proton on it, then you push it off as a water hurt. Okay, so you're not going to ever push off hydroxide here for sure. This is very much an equilibrium reaction than if I push off principle or something. This is the one where they radioactively label the oxygen and acid and trace it through. The classic question. Number 13, I see a carbonyl. It's an ester. I go and look for a nucleophile, and it's methoxide. So if I go with plan A, this is number 13. Plan A is attacking the carbonyl, and in this case, when I attack the carbonyl, I actually get a different ester. So this is A. A is a transesterification. I went from the rather challenging OR group with the ring on it to just a very boring one. Now I treat A with sodium methoxide followed by acid. So now I want to go to B. I see an ester. I see a strong nucleophile. If I attack here, open, close, whoosh, I can send things back. So what's plan B? Alpha hydrogen. So I'm going to make an enolate here, and it will attack itself. So you're going to do a place in condensation. What's the acid going to do? They could write the base, and then the acid, and then the heat in 3 separate steps. They could run it all together. They could put hydroxide with water, dilute acid, and heat together. I tried to write it in a lot of different combinations because I don't want you to be locked into memorizing one thing and then lost in it slightly different. So then followed by decarboxylation, or spontaneous decarboxylation, and you know you've already got a leg up because what normally follows placing saponification and decarboxylation. Do you know what shadowed out what saponification is and its reagents? Do you know what substances decarboxylate? Beta keto acids, not just every carboxylic acid, but beta keto acids. Just limited to that group. Okay, number 14. I see some carbonyls. They've got leaving groups, so I'm thinking mushy things. I look over, I've got a strong nucleophile, but when I attack the carbonyl, I get the same thing back. Plan A escapes. What's plan B? Alpha hydrogen. They're going to see these fabulous alpha hydrogens stuck between the 2 carbonyls. So I'm going to make an enolite, and in fact, here I'm going to get 100% enolite. So what is it going to do? Here it's going to do an SN2 reaction. This is the only trick, well, only one I thought that was really tricky. Tricky. On the whole thing. Like more of a homework problem than an exam problem. But I thought of it, I was like, oh, I gotta do that. I don't know how many carbons there are here, so we'll just put that many in. You get this? Okay. Then they follow it up with more base. So you're going to make another enolite here, and it's going to make a ring. So when you get done, you're going to get something. Now, I haven't counted my carbons, so bear with me. There. Okay. You're going to get a ring. Do you see the setup there? Normally when we're doing this reaction, you do base, followed by the SN2 reaction, base, followed by the next SN2 reaction. Now I see the base in the first SN2 reaction, and then I see the base. And there's nothing else to put in there. So you have to go searching for it. So I'd already built in the next substance. And you know what? Internal reactions that make 5, 6, and 7 member rings are fast. That was tricky. That's probably homework level where you're talking about group rather than spontaneously spew it out on an exam. Number 15, I see ketone. Attacking with hydroxide though makes me hydrate, so I'm very happy. So I make an alpha hydrogen, which side gets the enolite? Terminal does. Okay, what can it attack? Itself? No, all that bromine in it. So this is alpha halogenation. You're going to get 3 bromines over here on the methyl group, which is now a leaving group. Hydroxide attacks the leaving group. Opens it, closes it, pushes off the leaving group. It attacks the carbon. This is good. Check that one out. Shows up a lot of standardized tests, and it's almost always the methyl ketone which the whole thing off. And then number last one, 16. I see a ketone with a leaving group, so I'm thinking pushing. I go look for a nucleophile. I don't see any hydroxides. What do you guys see as a nucleophile there? Hydride. That's our hydride. So it's buried in there. Stronger with nucleophile. Strong. So I'm going to attack the carbonyl, open the carbonyl, push, close the carbonyl, push. I have an aldehyde. What do you think? Attack the carbonyl, open the carbonyl,